In this module, we will go over the process of learning parameters, i.e. training. We'll go over the total loss, or cost surface, and we'll go over how to obtain our parameters via PyTorch. Let's review the total loss, or cost surface. Symbolically, the true loss function looks like this. It's a function of the slope. The slope controls a relationship between x and y, and it is also a function of the bias parameter. The bias parameter controls the vertical offset of the line. In true linear regression, the loss function is a function of two variables, the slope and bias. We can plot it out as a surface. One axis represents the slope, and the second axis represents the bias. The height of the surface represents the value of loss generated by using that particular parameter value. Let's do a simple example. We have one sample point. y1 will equal 1, and x1 will also equal 1. We'll calculate the loss function. Now let's plug in two parameter values. A parameter for the slope of 0, and the parameter for the bias will be 15. The point on the parameter space is marked with the red dot. Calculating the loss, we get a value of 256. This is represented by the point on the surface, i.e. the height. Let's try another two parameter values. We try a parameter value for 15 for the slope and 5 for the bias. The value equals 361. This is the point of the surface, also represented by the height. The contour plot is a useful tool for understanding the loss surface. It's a bird's eye view of the loss surface. In this case, the horizontal axis corresponds to the slope parameter w, and the vertical axis corresponds to the bias parameter b. The contour line corresponds to points where the surface equals a particular value. Imagine slicing the surface at 200. We could represent this with the plane. The points where the surface intersects with the plane are equivalent to these contour lines. Similarly, consider cutting it at a value of 400, represented by the following plane. The points where the surface corresponds to the plane correspond to these contour lines. We cut it at 600. The points where the plane intersects with the surface can be represented by the following contour lines. To get a better idea of how our contour works, let's take a vertical slice of the curve at b equals 0. The resulting is a function of our slope. Let's take a look at this function from the following view. The following curve is a horizontal slice of our surface. It can be thought of as a function of our parameter w. Let's see what happens when we take some arbitrary cuts. We take the first cut, which has the following contour. We take the second cut. At this point, the curve is relatively steep. As a result, our contours are very close together. We take a third cut. At this point, the curve is less steep. As a result, you have to travel a far greater distance to reach the same elevation. As a result, the contours are much further apart. We can keep track of our parameter values by looking at different points on the contour line. Here's the first point at negative 15 and approximately negative 5. Here's the second point at negative 5 and 0. And here's the third point. We can see that the jump between the first and second point is a lot greater than the jump between the second and third point. The following plot shows the values of the parameters and the surface contours. The plot on the left shows the training points in red and the line generated using the values of the parameters corresponding to the points on the surface. After 2 iterations, we see the line does not really match the data points. We continue for a third iteration. The line gets progressively closer. For the next few iterations, the line gets even closer. We continue the process, and as a line approaches the data points, we approach the minimum of the surface. We can also view the data points as a surface where the height represents the total loss or cost. Each derivative is a change in a particular direction. The derivative with respect to the slope parameter reflects the change with respect to the direction w. The derivative with respect to the bias reflects the change in b. If we put these two derivatives in a vector, we get the gradient, hence the name gradient descent. The gradient points perpendicular to the contour lines, and gradient points to the direction obtained from the next iteration. As the points get closer to the minimum, the value of the gradient gets smaller and smaller.